So in this particular webinar, we will cover fundamentals of MATLAB programming by solving a specific problem. And the problem we are solving here is the automation of the process of finding solutions to systems of linear equations. And what we'll be using is the Gauss-Jordan Elimination Method. So what you have in front of you right now is, these are the case studies that we will be handling. We have 3 systems of linear equations and their solutions are already given there. This is the first one. Okay, it is 2 equations with 2 unknowns, and the correct solution here is x equals to 1 and y equals to 2. Okay, and here 3 equations, 3 unknowns, the correct solution x3, y2, and z1. And here 4 equations, 4 unknown, the correct solution, as you can see, is right here. Okay, so what's the purpose of this? The purpose of this is to use these 3 equations as benchmarks. It means that the function which we are going right now to create in MATLAB, that is supposed to automatically solve any given system of linear equation, we will have to try these case studies in that function to validate that our function actually solves any given, linear equation. I hope we are together on that. Okay, good. So to move on, good. So the Gauss-Jordan Elimination Method. What we are taking as case study to explain the Gauss-Jordan Elimination Method here is the second, is the second equation, the second system of linear equation rather. So this is what we have here. Well, the Gauss-Jordan Elimination Method tells you that if you have this system of linear equation, if you have this system of linear equation, you have to transform it into a matrix first, and the matrix consists of the coefficients of the different unknowns and the constants also. So look at this. Each row of the matrix represents an equation. So equation 1, will be row 1. Equation 2 will be row 2. Equation 3 will be row 3. The first column here will represent the coefficients of the x unknown. For equation 1, we have 2 as the coefficient of x. Equation 2, we have 1 as a coefficient of x. And equation 3, we have 0 because there is no x here. So we have 0 as the coefficient of x. And same thing, we have then y, 1 for the first equation, 4 for the second, 3 for the third, and then lastly z, 3, 5, negative 2. So this is called an augmented matrix because normally if you have a coefficient matrix, we will stop there. But an augmented matrix includes the constant terms, that means the terms that are found on the other side of the equality. So we have the constant terms which are 11, 16, 4. So we have to transform this equation into an augmented matrix of this form, Then we will need to conduct a series of elementary row operations to be able to transform this matrix into its row reduced echelon form, which we have right here, And the goal is to have such a matrix where we have the identity this way and some constants, knowing that if we transform this back to the equation, having this same logic, then we must have found exactly the value of x to be 3, the value of y to be 2, and the value of z to be 1. Hope that makes sense up to now. The following operations on the equation, so what we call elementary row operations now. Let's understand what that is. So elementary row operations are actually operations which, when conducted on a particular system of linear equations, it will yield an equivalent system of linear equation, but 2 of them will have the same solution set. Actually, equivalent system of linear equation means that they have the same solution set. So there are actually 3 basic elementary row operations. The first one states that if we multiply an equation by a constant, to form a new equation, then we must have formed another system of linear equation which is equivalent to the first one, means the 2 have the same solution set. So as an example, this is our original equation, okay? So if we multiply row 3 by -2 to have a new row 3 here, where all the elements are multiplied by -2, so we have 3 here to give us -6, -2 times -2 to give us 4, 4 times -2 to give us -8, then this will be the new system, right? Row 1 has not changed, row 2 has not changed, but row 3 here is different, okay? So these two systems here are equivalent. Why? Because they have the same solution set, okay? So basically, with what we are looking for, we have not changed anything, because at the end of the day, to solve this system, we are looking for x equals 3, y equals 2, and z equals 1. Therefore, if this is what we find here, we have no problem. Okay, so that's the first rule: multiplying an equation by a constant. The constant is in the set of real numbers. So the next rule is adding an equation with another to yield a new equation. Okay, so this is what we have as an example this way. If we go ahead to form this new system and add equation 2 to equation 3 to form a new equation 2, which we have this way, then we have not changed anything with respect to the solution set, okay? These two systems are equivalent. So let's look at how we conducted that. This is equation 2, equation 3, here they are. So x, here the coefficient is 1, plus 0 will still give us 1. This is the one we are having, okay? 4 plus 3 will give us 7, this 7 we are having. And 5 minus 2 will give us 3, this is the 3 we are having. And then 16 plus 4 gives us 20. Okay, so on your time, you can still try and replace this x equals to 3, y equals to 2, and z equals to 1 in this equation 2 to see that actually it's working. Okay, it satisfies that equation. So this will still be an equivalent system. Okay, and the last but not the least elementary row operation is exchanging two equations. This is so obvious, right? So if we are in this equation and I exchange row 1 by row 2, then this is what I get, and the solution set is exactly the same thing. Okay, so these are the operations that we shall be using actually to somehow, okay, to be able to transform this augmented matrix into its reduced row echelon form, which we have right here. Okay, so that we can get from there the values of x, y, and z. So let's see how we'll go about that now in detail. Now, this procedure is not necessarily the procedure par excellence, but it is what we shall be implementing. This is the procedure that you should have in mind, because this will lead into the logic that we shall be using in the MATLAB programming. Okay, so here, this is our goal. Our goal is to transform this matrix. Okay, remember, every equation here is a row. Okay, our goal is to transform this into this. That's our goal, because when we have these, okay, we'll have the values of x, y, and z right here. The way we do that is by applying a series of elementary row operations, knowing that those row operations will never change the solution set. Okay, we will still have the same solution set as we go along. So this is the way we will proceed. We will have to proceed column by column. So it means whatsoever we are doing, we have to go one column after the other. We start with x, then y, then z. Okay, so the columns that we're concerned with here are the columns that have the unknowns. Okay, that's all. We don't deal with the column of, as you can see, this is the identity that we are trying to produce here. Okay, what is the outcome here is actually the result of all the operations that we've conducted this way. Good. So once we are in a column, the first thing we have to do is to identify the elements in the main diagonal within that column. Okay, then we'll need to multiply the row of that element by the element's inverse, so that one remains the element in the main diagonal. So you shall be seeing that practically, don't worry. And then take the element row as reference to conduct elementary row operations with the other rows, such that every other element in the column except the main diagonal is 0. So this one is just a big grammar for nothing. So let's go ahead and see how it is acted upon practically. Good. So let's start. This is our original matrix, okay? The first procedure is we start with the first column. This is the first column here. On the first column, we identify the element in the main diagonal. This is our main diagonal right here, okay? The main diagonal is a diagonal that has the same number of rows, where the elements have the same number of rows and the same number of columns, right? So this is our main diagonal. We identify within the column the element that is in the main diagonal. In our case here, for the first column, it is 2, right? Next, we need to multiply the elements row, the row of the 2, right, by the elements inverse. The inverse of 2 is simply half. It's simply 1 on 2. The inverse of a number is simply 1 divided by the number, okay? So we multiply the whole row, not to say that we divide it by 2, okay? That would be simple English. But in our elementary row operation, we say if we multiply. So that's why I'm using the term multiply by the inverse of the element to obtain a new row, okay? So focus on this terminology. When we are on this line right here, these numbers colored here don't represent actual numbers, okay? The blue here is to represent the equations on this side, and the red here is to represent the equations on this other side. So here, the red one here will stand for row 1 this way, and the blue one here will stand for row 1 this other way, okay? So we will conduct an elementary row operation. We will multiply this row 1 by the inverse of the elements on the main diagonal, okay? The goal is to have our first one right here, okay? And the others will change. So 1 divided here, 1 divided by 2 to 3 times half, 3 on 2, 11 times half, 11 on 2. So this is our result. So this is the new matrix we are working from. Remember, applying elementary row operations will imply that these two matrices, this and this, okay, will have exactly the same solution set, right? Good. So to move on in our algorithm, we are still on the same column, okay? So basically what we want to do, let me try to say it a bit differently. What we want to do is, when we are in this column, for example, right, we want the main diagonal to be 1, and then everything that is under that 1 should be equal to 0. When we are here, we want the main diagonal to be 1, and everything that is above and below it should be 0. And finally, when we are here, we want this main diagonal to be 1, and everything that is on top of it should be equal to 0. That is our goal. Okay? Good. So, that being said, I hope that makes this step clearer. So, the next thing, we have this matrix now. This is our new matrix, which is, which is this one right here. Okay, good. Now we want to actually eliminate this one, right? We want to make it to be equal to 0. How do we proceed? Very simple, right? It's just to conduct this minus that. So this row 1 becomes the reference with which we have to conduct elementary row operations on the two other rows in order to have 0 and 0 right here. So we have the new row 2 has to be equal to the previous row 2, okay, plus 1 times negative 1. Why? Because we want to make sure that there is 0 here. Okay, we don't care about how these other ones will add up. We just want a 0 to appear here. Okay, so we will multiply here by here by negative 1, and then add up so that 0 can be the result here. And that is what we have here, right? So we have 1 minus 1, 0, 4 minus half, 7 on 2, 5 minus 3 on 2, 7 on 2, 16 minus 11 on 2, 21 on 2. So that's clear. And we done another step for this row 1. Why? Because on row 3, for this column 1, sorry, because on row 3, we already have a 0 right here, right? We already have a 0. No need to conduct any other operation there. It is automatically satisfied. Good. So Moving to the second column, we have finished with the first column, right? This is the outcome. This is what we want. We want 1 here and then 0 under. Now we move to the second column. Again, we apply our algorithm. The very first thing we do is to identify the element of the main diagonal. This is the element right here. Once we have done that, we multiply that row by the inverse of that element, okay? So that we can have 1 at this level. So the inverse of this will be 2 on 7. So that 2 on 7 times 7 on 2 will give us 1. Okay, that's why we multiply the new row 2 will be equal to the previous row 2 times 2 divided by 7. Okay, so this will yield us 2 on 7 times this to give us 1, 2 on 7 times that to give us 1, 2 on 7 times this to give us 3, right? You do the maths, right? So it should be easy. So if we follow this same process all through, okay, our goal now on column 2 here, for example, we maintain row 2 as our reference, and then we have to conduct an operation on row 1 such that this half here becomes 0. What do? We simply multiply here by negative half, okay, and then we add these two to form a new row 1, right, which is here. So 1 minus that, it will not change because here is 0, okay? But then half minus half will give us 0 here. 3 on 2 minus half will give us 1, okay? And then 11 on 2 will give us that. So if we follow with this system, okay, excuse me, this is the new matrix, and we are continuing with this way, right? We now need to remove what? This 3 here. We simply multiply this by negative 3, and we do the addition, right? So that we will have 0 right down here. Okay, so finally, we'll go to our third column, okay? And on the third column, we identify the element in the main diagonal, which in this case is -5, right? So having -5 is the same thing again. We multiply by the inverse of that -5, okay, to say, okay, we multiply. So we multiply by the inverse of that -5, and then we will get 1 here also on the main diagonal, and we can continue. It is the same process right till the end. Okay, so finally we will obtain this, okay, to conduct this in order to eliminate this last one, okay, and then we'll have our identity matrix right here and our solution 3, 2, 1, okay, which we can then revert back to the equation. So I think this equation rightly corresponds to what we had right up, right? The solution set, you remember. Okay, let me go there, let me go there. Good. The solution set, which is 3, 2, 1. Okay, so that's cool. That's cool. Till now, that's cool. So this procedure should be mastered and it should be understood, okay? Because this is what we shall be applying now in MATLAB, okay? So we are going to MATLAB at last. Normally, I was supposed to show you how to get MATLAB online for free during the webinar, but I foresaw that this webinar may take longer than I actually estimated. So I tried to cut down on some tasks somehow. So with this PowerPoint, you will have on this page, you have links, okay? These links here are meant for you to go and study as we'll be going along, okay, for you to go and study what we shall be touching detailedly and understand them better, okay, so you will have a framework to be able to understand all of these things. So here is a YouTube video that I actually uploaded, okay, that will lead you to go ahead and will lead you to get the MATLAB online for free, okay? MATLAB online and MATLAB free for 30 days, okay? We are not hackers, we are not crackers. So they offer a free trial to everyone for 30 days. So if you click on that link, you will be able to go to YouTube and there's a video waiting for you there that will show you how to use MATLAB even right on your browser without needing necessarily to install it to your computer, okay? And all of these other things, whether it is entering commands in MATLAB, creating matrices and arrays, create and edit variables, matrix indexing. These are things that we shall be seeing now, okay? But we shall be seeing them as much as they concern the problem that we are trying to solve. So for detailed understanding on them, all of these on this page are links that will enable you to understand those concepts better, okay? Good. So that being said, I think we can dive right into MATLAB. Right now we are in MATLAB, and the version I'm using right here is version. Oh, sorry about that. The version I'm using right here is version 2018. Okay, R 2018, MATLAB 2018B. Good. I hope some of you have seen MATLAB before. No, I do not actually expect some people to have seen MATLAB before. Well, this is MATLAB. Let me present MATLAB to you officially. This is the interface. Okay, I will not spend time talking about the elements of the interface. I will be explaining those elements as we are going along. So remember our goal in this webinar. We want to create a function that will actually automatically calculate the solutions of systems of linear equations using the Gauss-Jordan Elimination Method. Okay, so how do we go about it in MATLAB? The very first thing I would like you to know about MATLAB is that where we are here, okay, is called the command window, as you see the name right there. And this command window, you can look at it as a big calculator somehow. This is where MATLAB is waiting for your commands, okay, in order to execute them automatically. What you see right here, okay, is what we know as the prompt, okay? So when you see these two arrows, it means MATLAB is there and he is bored because he is waiting for a command to execute. And so far, we are not giving him any command to execute. That is why that thing is tickling like that, reminding us to write and type something. So you have to see this as a calculator. MATLAB is meant for engineers mostly, so it is meant for computational engineering stuff somehow. So calculator, if you have, all of us have used calculators before, that one is sure. And on the calculator, you have basic operations: addition, subtraction, multiplication, division, exponent, right? Those are basic operations that go even with the BODMAS principle. So in MATLAB, if I want to use this as a command, as a calculator, for example, let's say, I don't know the multiplication of 8 by 4, very trivial, but let's assume I don't know it and let's get MATLAB to do it. So I will just go ahead and say 8 times 4. So this times here is the star symbol, okay? In MATLAB, to do multiplication, you use the star symbol. If I press enter, the answer is there immediate, 32, okay? 32. And if I want to do 9 plus 6, for example, the answer is there. 8 minus 3, the answer is there. What is left? Division, 4 divided by 2, the answer is there. What next? Exponent, 4 to the power 2. The answer is there, 16. Okay? So you can use MATLAB for any complex calculation, okay? And even the BODMAS principle, if you have something like bracket 5 plus 4, all of that divided by 5 times for etc., and you type enter, the answer is there, okay? So look at MATLAB, basically this command window, as a calculator. It will function exactly as a calculator. So somehow, if you know how to use a calculator, you know how to use MATLAB for calculations, okay? That's already a plus for you, okay? And congratulate yourself on that. And the next thing we shall be looking at is just look at the way the interface changed somehow when we were typing the commands, okay? Something was created here known as ANS, okay? If I do 4 plus 5 now, and I press enter, what happens? you have the ans here that has changed to 9. It tells me ans is equals to 9, and the ans here has changed to 9. Let's try something else. 7 times 2, enter. Ans is equals to 14, and the ans here has changed to 14. What does that tell you? Each time you conduct an operation in MATLAB, okay, the answer or the execution of that operation is automatically stored in a variable that MATLAB creates called ans. So it just say ans there stands for answer, okay? So it means the answer of your operation is equal to 14, and it is stored there. But if I go ahead and say a plus 5, it takes on the answer of the new operation. It is no longer 14, it is 13. It means this 14 has been lost, and this 9 as result has been lost. But there comes a time where I want to store all of these answers, for example, because I need to use them somehow, somewhere. So we enter into the concept of variables in MATLAB, okay? So if I want to store, let me say I have 8 plus 5. I want to store this answer, and I don't want to lose it. How do I go about it? Just have to do maybe x is equal to 8 plus 5, and that's it. Okay, I have created what we call a variable, okay, and it has taken on the answer 13, which is the result of my operation. Now, what is a variable? A variable is a name, okay, that we give to the memory of our computer in order to store some data which we can remember, okay? So when we call that variable the way I will say x here and we press enter, the data that we stored in the variable, which is 13 in this case, is restored and given back to us. And we can use that data that we have stored to conduct other operations. So I can say, for example, x times 2, and it gives me what? The 13, which is inside, times 2, which gives us 26. Okay? And as I created the variable, what happened? X added itself there. So this enables me to present to you what the purpose of this window. It is known as the workspace. The workspace gives you an inventory of all of the variables that you've created in MATLAB and that you are using or that are available and accessible to you throughout this session. And it gives you the values that are stored within each of those variables. Okay, so there are norms to create variables in MATLAB. You don't just create them anyhow. Okay, there are norms to do that. Every variable is supposed, a variable name is supposed to start with a letter. Okay, it cannot start with a number, it cannot start with a special character. I can't say 4r or 5r is equals to 4, for example. It does not make sense. Okay, and it tries to correct me. Did you mean r is equals to 4? Because it expects my variable name to start with a character. But on the other hand, I can say r5 is equal to 4. That is acceptable. Okay, so every variable name must start with a character, okay, and it can be followed by a combination of characters and numbers in any order. Okay, if I say r5a is equal to 4, for example, it recognizes as a variable name. There's no problem. This is in r5a created, and it has a value 4. No problem. Okay. Okay, good. So the other thing you should know is that variable names don't accept special characters. I can't say e space o is equals to 5, for example. Okay, that doesn't make sense, and MATLAB is even resilient to answer that. Okay, so it tells you undefined function or variable e. It's trying to look for it in its database, but it cannot find anything corresponding to that. So good. Okay, so the only special character that is permitted, so all this ampersand, hyphen, apostrophe, all of those are special characters. Dots, they are special characters, but they are not allowed, okay, in MATLAB. They are not permitted. So the only special character allowed is the underscore. I can say E underscore O equals 5, and it will go just fine, okay? So again, to create a variable name, you start with a letter. It can be followed by a combination of what? Underscore 8, number or character. Okay, so this is important. This is very, 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 very important. Good. So we've created all of these variables so far, and by now you understand what the workspace does, right? Practically. If I had told you that this is what the workspace does in the beginning without creating variables, it would have been cheap talk, or in fact wasted talk, because I'm sure many will not have been understanding. Okay, so that being said, the next thing is, you notice each time I type something here, things are changing this way, right? So look at this. Y is equal to 5. Enter. Y is equals to 5. Okay. P is equal to y plus 2. Let me fill. P is equals to y plus 2. So everything I type in the command window and I press enter, what happens? It is reproduced here. This is known as the command history. Okay, so the command history stores your commands written in the command window in the order in which you wrote it. Okay, and you can navigate the command history very, very simply, because many times when you program in MATLAB, oh my God, so many times when you program in MATLAB, you want to come back to the commands that you've been executing. Okay, so for that, if I want, for example, to redo this R5A is equals to 4, right? Without having to retype R5A is equals to 4, I can navigate. Actually, now I am pressing the up arrow key on my keyboard. Okay, so when I press down, let me start all over. When I press up, it is P is equals to Y on 5. Up again, Y is equals to 5. Up again, CLC. Up again, this one. Up again, that one. Up again, and so on. I hope you see that. Okay. So if I press down, it goes back to CLC. Down. Okay. So these are the up and down keys. You can navigate them on your command prompt. Okay. And get whatsoever you want to get. Good. So that's the command history. Okay, simply stores everything that you've been doing. So for this other side, we are still coming to that. Okay, we are not yet there. So with that brief introduction, oh, let me say something. Come on. I have been doing it without saying it, and you guys too are not talking. How you talk? Okay, again. Oh my God. Okay, let me just do something. Good. So if I have used up my screen the way I have just used it several times, okay, and I want to start all over, I want to have a fresh page so that I can rewrite again, okay, you just use the CLC command, okay, it stands for clear screen, and you press enter, okay. I don't need all of these variables again with where we are going to, okay, so in order for me to delete them, I just need to press the clear or type the clear command and press enter. Okay, so that's where we are for now. Okay, so let's go back to our Gaussian elimination method, and we want to solve that second system of linear equation. I wrote it for us somewhere here so that we don't get dancing around pages. This, don't worry about this for now, okay? Don't worry about this. It does not enter the scope of this webinar. But this is our system here, okay? You recognize it. This is it right here, okay? So the first thing we want to know with our Gaussian elimination method, solving it in MATLAB, is first of all how to create a matrix, okay? Because we need to convert that system of linear equation into a matrix, augmented matrix, but a matrix. MATLAB actually stands for matrix laboratory, okay? Everything, you will be amazed that everything in engineering and science can actually be modeled in form of matrices. It's magical, it's outstanding. But MATLAB stands for matrix laboratory. It means that no matter what you are dealing with, no matter the problem you have to solve, you have to somehow convert it into a metrical problem in order to execute it in MATLAB properly. And with the experience I'm having so far, I've come to understand that there is nothing, literally nothing, that cannot be modeled in metric format. It's just for you to have that skill to be able to create your world. Okay, so excuse this separation of screens. Just focus on this for now. Okay, we will look at this one a little bit later on. So we want to create a matrix. How do we go about that? Well, it's very simple. Okay, the very first thing to do is to open and close the matrix. This is what tells MATLAB you want to start creating a matrix. Okay, this one, and this one tells MATLAB you have ended the creation of your matrix. Now, to create the matrix itself, you go row by row. Okay, so you start with the first row, you create all of its elements, then you move to the next row, you create all of its elements. This is the matrix that we want to create right here. Okay, this is the matrix we want to create, remember. So we go row by row. We start with the first equation, we finish all of its elements, then we go to the next row, we finish all of its elements, we go with the next, we finish all of its elements. That's how simple it is. So here, what is the first element here? 2. Okay, now to separate the elements of the column, okay, we simply use comma. Okay, so it will be 2, comma, 1, which will be the coefficient of y here, comma, 3, the coefficient of x here, comma, 11, the constant. This will form our first equation, which is the first row of the matrix. Okay, to move to the next row, you just press semicolon. Okay, now semicolon takes you right here. Okay, so you can start again. 1, comma, 4, comma, 5, comma, 16. Okay, then we move to the next row, which is this last one here. Okay, to move to the next row again is semicolon. Okay, so you see how simple it is, right? It's a simple logic. Yeah. So you have the coefficient of x, which we are not seeing here, but which we must put here, which is 0 for the matrix to be consistent, comma, we have 3 for the coefficient of y, comma, we have -2, okay, for the coefficient of oh, this is a mistake, right? This is a major mistake. Here is not y, it is z. Okay, sorry about that. So we have -2 for z, and then we have 4. Okay, and when we press enter, that's our matrix. You see that? So check that out for yourself. Okay, 2, 1, 3, 11, 1, 4, 5, 16, 0, 3, -2, 4. Clean. Is that so? Good. It means we finish with this. Okay, we can come back to our normal command window. So this is the matrix that we want to transform. This is the matrix that we want to transform into its row reduced echelon form. Okay, so right now, what do we notice? We notice that the matrix is still stored in our hands. Okay, so we want to create a variable which we will call a to be able to store the value of this matrix. But then at this level, guys, I don't want to retype all of that matrix again. I don't even want to copy here and paste. So what I will do, I'll just navigate through my command window. I will just press up and then come back, okay, and a is equal to, and that's what I'm having. A is equal to that. So it means if I call back A, that's what we are having. Okay, good. This is what we are supposed to work with. Now we have to start our process. Okay, now in MATLAB, matrices are characterized by their sizes. In MATLAB, like in mathematics, like in everything, okay, it is a rectangular arrangement of data, okay, with specific number of rows and specific number of columns. Each row has a significance, each column has a significance, okay. So here we know that row 1, row 2, row 3 represents equation 1, equation 2, equation 3. Is that so? And column 1, column 2, column 3 here represents the coefficients of x, y, and z. And then the last column represents what? The constant. It has a significance. But then, this row, as you'll see here, MATLAB no longer gives you the value per se. Okay? What it gives you is the size of the matrix, which is 3 by 4. Okay? So, if I type rows, of A, we should be able to get the characteristics of that particular variable A. Okay, rules will give you the characteristics of any variable in terms of this table. What is the name of the variable? What is the size of the variable? What is the space it occupies in memory? What is the class of the variable? What are the attributes of the variable? Not covered in this code. But then A is a 3 by 4 matrix. Okay, and it occupies a space of 92, and the class here is double. In MATLAB, we have single and double for real numbers representation. Okay, these are the classes for real numbers. Double, you use double when you want to represent a very large scale of numbers, and single is a smaller scale. The numbers that go beyond those scales is what we know as inf. Okay, there's actually something known as inf in MATLAB that stands for infinity. Okay, but I digress. Let's come back to what we have to do. So another way for me to be able to determine the size of this matrix will simply be to use a built-in function. Okay, the name of the function is size. In MATLAB, the good thing about MATLAB is that most of the times, if you need a function that executes a particular command, okay, most of the times, if you know the English name of that function, if you know the mathematical or scientific or engineering name of that function, many times the built-in MATLAB function name is very close to that same name that you know. For example, we want the size of the matrix. The name of the function is size. How beautiful is that? Okay, that's the name of the function. Okay, but we need to somehow indicate to MATLAB that we want the size of the matrix A. Okay, so the concept now of input argument comes in. We open these brackets, okay, and inside MATLAB expects the matrix, okay, of which we want the size, and this matrix is simply A. Okay, so we are telling MATLAB, give us the size of A. Enter. So it gives us another ans, okay, which is the answer of this execution. But ans this time is what? 3, 4. What will you notice? There is a bracket here and there is a bracket here. So this is actually a matrix, what we know as in MATLAB as a vector. Okay, this is a row vector. It has just one row but no column. One row and 2 columns, but it has just one row. That's why it's a row vector. Okay, so it is 3, which represents the number of rows 1, 2, 3, and 4, which represents the number of columns 1, 2, 3, 4. Okay, so if we want to know only the number of rows of this A, there is another extension of this same function. We will say size of A, comma 1. The 1 there is to represent the first dimension. We want to know the number of elements in the first dimension of A. The first dimension is the row dimension. When I press enter, I will have 3. Okay, if I say 2, then this will be for the second dimension. Okay, then that will be 4. Hope we are cool till here. Good. So CLC. So we have our matrix A. What did we say we are doing in the Gauss-Jordan elimination method for the first step? We have to actually identify the first element. This is our first element, right? But then we are in MATLAB. How do we retrieve this first element as an independent value, okay, that we can use? Because remember, the next step will be to multiply the whole of this row, right, by the inverse of this element. Is that so? But let's first of all see how we can actually index and get this element as an independent entity. Okay, every element in this matrix, whether it is 2, 4, 5, and all the like, they are all characterized by the position they occupy within the matrix. So number 2 here, for example, is in row 1 and column 1. Number 5 here is in row 2 and column 3. Number 16 here is in row 2 and column 4. Okay, so let's get those numbers now as independent entities. Let me say the first one, I'll call it let me call it A here. Why not? A should be equal to, we want A to be equal to this first item here. What do? We simply index. To index, we'll give the name of the matrix, okay, or the variable name that contains the matrix, and we open brackets, okay, to say within this matrix, okay, we want the value contained in the first row, comma, the first column. Okay, so we put the values, that the positions that we want for the first dimension, the positions that we want for the second dimensions. And when I press enter, what do I have? A is equals to 2, because 2 is the element that is contained in the first row and the first column of the matrix A. So in that same line, let's get the value 5 and we'll call it B. So B will be equal to A of what? We want the second, okay? This is the second row, 2, comma, what? The third column, 3. And I will have the value 5. It is important for us to know this, and you will understand why later. So let's get our last one. What was it? Was it 4? Yes, let's say 4. C is equal to A, and I'm sure now you can flow along with me. You have A of, can you guess? 3, comma, 4, right? Okay, that's 4. I hope it's 4 we're looking for. Yeah, it's 4 we're looking for. Good. So, still in line with this indexing, there is a time where we will need, for example, to multiply, as we said, this row, just this row, right, by by a particular number, let me say. So we will need to actually be able to index this row, okay, the whole of the row. How do we do that in MATLAB? If I want the whole of this row, well, all I need to do is to say A of, okay, the first row, comma, 2 dot. So this 2 dot here is to indicate that I want all the columns of the first row. Okay, that's what it means. 2 dots means all the columns of the first row. So if I press enter, what will I have? I will have an answer which is 2, 1, 3, 11, which is all of the first row of the matrix. If I want the third row, all I need to do is 3. Now, just to extend, what if I want, for example, this third row right here? Okay, how will I go about it? This third column, rather, right here. It's the same principle in the other direction, right? It will just be A. I want all of the rows of what? Of the third column. And when I press enter, I have my 3, 5, negative 2, 3, 5, negative 2. Okay? So another concept still on indexing is if I want the last, let me say I want the last row in any given matrix. I don't care the size of the matrix and all the like. Well, MATLAB enables you to have that. If I say, for example, A of end, okay, comma, 2 dot, this end here stands for the last row, okay, of this matrix A. Okay, so if I press enter, it is the last row, this one. And if I do it the other way, it will be the last column, okay, always. So 11, 16, 4. Good, we are cool with that. Another thing that we need to know now, let's say I want to, I've made a mistake, okay, in creating this A. Before doing that, because I don't want to lose the value of A, I will ascribe the same matrix A to a certain matrix B, which is here. Okay, so now let's be using B to do our experiments before coming back to A. Okay, so this is B. Okay, so let's say in this B, I made a mistake. Okay, I want to replace all of these elements here. I want to replace them. It's supposed to be 1, 2, 3, 4, not 2, 1, 3, 11. Okay, we're just using that as an example to understand some things. So what will it be? It will simply be, to do that, I will have to index the position that I want to change, which is this one. Okay, how do I index that? It is the whole row, right? So it is B1, comma, column, which is the whole row. Okay, so I'm saying B1, comma, column, the new value that should be given to it should be equal to, okay, and I have to create what? A matrix that is the same as this one. So what will happen is that it will replace element by element. So I'll just say 1, 2, 3, and 4. Okay, so what will happen? It will come here. 1 will replace this 2, 2 will replace this 1, 3 will replace this 3, oh, and 4 will replace this 11. Okay, and that's what I'm having. I'm having a new B where the first column is 1, 2, 3, 4. I hope you see where we are already going to with this, right? Where the first column will be 1, 2, 3, 4. Just to show you another trick. Imagine that I wanted the same value all along that line, okay? Or let me say the second line for experimentation purposes. Okay, I want the same value. I want it to be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, all I need to do is equals to 1. Okay, when it's the same value, you don't need to create a matrix and put 1 everywhere. You just say is equals to 1, and 1 will be distributed all along. Matrices in MATLAB have a very, very special relationship with scalars. Okay, scalars have the habit of affecting all of the elements of the matrix simultaneously. So from this indexing, what we will do now, we will move to matrix operations. And after the matrix operations, we will be able to conduct some things with regards to our Gauss-Jordan elimination method. Just some things, okay? Before entering again a little bit deeper. Okay, so far, so good. We saw in the beginning that you can use MATLAB as calculator, plus, minus, times, and division. We saw that in the beginning, right? Well, matrix operations is the same thing, okay? It's the same thing. It follows the laws of linear algebra, okay? To add two matrices, let me say this is A and this is B, right? To add two matrices, what happens? All of the entry of the matrices are supposed to add themselves. So if I want to add these two, it's just A plus B, okay? And what happens? As you can see, 2 plus 1, 3. 1 plus 2, 3. 3 plus 3, 6. 11 plus 4, 15. Okay. 16 plus 1, 17. It adds element by element. To subtract is the same, exactly the same deal. Okay. To subtract is A negative B. Matrix multiplication, as you know it, holds true. Okay. For everything I'm touching here, remember, oh, oh. What happened? Good. We are coming to this. But for everything that I touched so far, wow, thank you, Dr. Mauricio. Okay, so for everything that I have touched so far, you should know that there are references. Okay, the links are there in the PowerPoint. You will just click them and you'll be able to read and execute them all by yourself. Okay, so no problem. Now, we did A times B here and it gave us this error. I'm sure those who know how to multiply matrices can tell, right? Why? Because the size, what is the size of A? The size of A is 3 by 4. And what is the size of B? The size of B is 3 by 4, right? So we cannot really multiply 3 by 4 and 3 by 4. Why? Because the number of columns in the first is not equal to the number of rows in the second. On the other hand, we can do B times A. Is that so? No. Why? Because the number of columns of B is not equal to the number of rows of A, okay? But if I transpose this, okay, everything works fine. Great. But that is not our focus, right? That's not our focus. So let me just take advantage and just introduce that concept too. We're not supposed to see it, but there are bonuses everywhere, right? So to transpose this matrix in MATLAB, okay, you just need to say A dot transpose. The dot there is important, okay? A dot transpose. And this gives you the transpose of A. Let me say it. MATLAB is meant for engineers. Anything you can possibly imagine in mathematics and all the like has a corresponding function in MATLAB. Somehow, somewhere. It should have it somewhere hidden in MATLAB. Okay? Even what we are trying to program now, I'll give you a surprise at the end of the day. Okay. So, good. So we've seen we can add matrices, you add element by element. We can subtract matrices, you subtract element by element. To multiply two matrices, what happens? The law has to be respected. The number of columns in the first has to be equal to the number of rows in the second. To divide two matrices, okay, to divide two matrices will actually introduce the concept of inverse of matrices. Okay, so another way we could solve that equation, you know that our equation, right? So let me say A, this is the equation. Is that so? This is the equation we're trying to solve. You remember that we have the equation ax is equal to b. You know that style where x is what we are looking for, b is the constant vector, and a is the coefficient matrix, right? And we are looking for x, right, such that what x will be equal to a inverse times b. That will be the solution. Okay, so if we have to apply it here, how will we go about it? What is the coefficient matrix in this? The coefficient matrix is all of this, right? Is this part. That's the coefficient matrix, the coefficients of x, y, and z. Okay, so can we index that? Let's go ahead and index that. So to index that, I will take I'll first of all start with the columns. All of the columns, we have 1, 2, 3. Is that so? Yeah, it takes all of the columns. So I just need to put that for all of the columns. But for the rows, it goes from row 1 to row 3. And there is a way of writing that in MATLAB. Okay, I can choose. I can open this bracket and create a vector that will actually index those positions. 1, 2, 3. This is the long way to go about it. Okay, the short way to go about it will simply be, since they are going from 1, 2, 3, they are in that order, I will just take 1 is to 3. Okay, so before I even write that, let me copy so that I don't forget. Let me introduce that notion so that you're not completely lost. If I say 1 is to 5, see what it gives me. 1, 2, 3, 4, 5. Okay, so it will give me all the numbers from 1 to 5 with an increment of 1. That's another way of creating vectors very, very rapidly. We will see this in this very webinar when we'll be dealing with the for loops. Okay, so if I say 8 is to, let me take a number less, that does not go. It's an empty matrix. Okay, why? Because there is no way you're going backward. It does not make sense. Okay, you have to go from the smaller number to the larger number. Okay, so if I say the 1 is to 3 there, okay, you understand that it's the same as creating the vector 1, 2, 3. Okay, it's exactly the same thing. So now you understand what I am doing. So let's go back, and this is what I'm doing. So what I'm saying is that if you want to index different positions, okay, let's just take an arbitrary example. Let's say I want to come out with a matrix that is 1, 4, and then 11, 16. Okay, so what I'll do, or rather, let me just say 1, 3. Okay, 1, 3, and then 11, 4. What I'll do is that at the level of the rows, I'll indicate all of the positions of the rows I'm concerned with. So 1, 3 is on which is on the first and the third row, right? So it will be 1, 3, and I close, comma. Now, at the level of the column, what are the columns I'm touching? I'm touching the first, the second, and the fourth column, right? So I'll just open second, comma, fourth column, okay, and close this, and that's what I'm having. 1, 3, 11, 4. This indexing is so flexible. All cannot be taught in one webinar. But again, I have sent you the PowerPoint with all the links where you can get the details. So let's go back to what we were saying. We have a, okay, we wanted to get the coefficient matrix, right? Good. So the coefficient matrix, I want all of the rows, okay? But here, what do I want? I want just 1, 2, 3. That is my coefficient matrix. 1, 2, 3. Is that so? Good. Now, my constant matrix on the other hand, okay, is supposed to be what? 11, 16, 4. Okay, so this is my coefficient matrix. No problem. My constant matrix is supposed to be who can tell me how I will do that? I can just say all of the rows again, right? Comma, what? End. Okay, that will be the last column. Is that so? So in MATLAB, in order to solve that problem of inversing, okay, we will use what we call the back division. Are we together? So we will take the coefficient matrix and we will do a back division by the constant matrix. Okay, and we will press enter. That is the result we expect, right? It is 3, 2, 1. That's the solution actually of our linear equation. You remember that, okay? So this is the way you inverse a matrix. This backward division implies that it is actually this divided by this, not the other way around. It's actually this divided by this. Remember, our normal division is 1 divided by 3. This is the way it is, okay? So this back division inverses things, and this is what you use for matrices. This is what MATLAB recommends if you have to inverse a particular matrix, okay? But I digress. Let's go back and continue with our Gauss-Jordan elimination method. So we were still on matrix operation. We've seen how to add matrices. We've seen how to subtract matrices. We've seen how to multiply matrices. We've seen even how to inverse matrices and multiply it with another. But then there are other operations on matrices which I want to show you. So, for example, if I have, this is my B again, okay? There is a way of multiplying these two matrices as if you are actually adding them. So it means you're doing what we call an element-wise multiplication, okay? So to do that, it is A dot times B, okay? So if I press enter on this, what happens? 2 times 1, 2. 1 times 2, 2. 3 times 3, 9. 11 times 4, 44. 1 times 1, 4 times 1. You see that? So that is element-wise multiplication. It will multiply element by element. You can also do an element-wise division, okay? Which will do exactly the same thing. Just press dot. And when you see none here, it means that this number here, it was wanted to do 0 divided by 0. It does not exist, right? So none in MATLAB stands for not a number. That's how MATLAB represents numerical data that are not supposed to be numerical data. So it's simply not a number, okay? Good. The other last thing I would like us to see now before actually getting to MATLAB. Okay, Sandrine, is now you understand? Okay, so the other thing is how matrices actually operate together with constants. Okay, so say I have a constant 2, right? Okay, let's put our matrix A back on the scene. If I multiply just like algebra, if I say 2 times A and I press enter, what happens? This 2 multiplies all of the elements of A. Okay, so it is 2 times 2, 4, 2 times 1, 2, 2 times 3 is 6. You multiply all of the elements of A. Okay, if I say A divided by 2, okay, what happens? Again, it's the same thing, okay? The A will divide all of the elements, or the 2 rather will divide all of the elements of A. Okay, hope that's clear. Now, the other thing that will not be in linear algebra, for example, is if I say A plus 2, it's a different ball game, right? In this case, 2 will add all of the elements of A. That's the relationship you have with matrices and constants in MATLAB. Constants many times affects all of the elements of the matrix in the same way simultaneously. Okay, so A plus 2 will give you 4 plus 2. Okay, will give you rather 2 plus 2 to give you 4, 1 plus 2 to give you 3, and so on. Okay, A minus 2 will do exactly the same thing. Good. So all of what we've said so far is enough for us to start doing some things with respect to the Gauss-Jordan elimination method. So let's go right ahead. This is our matrix, right? So first thing, we start with the first column. This is the first column here. In the first column, we want to identify the first element. Is that so? What will be the first element? The first element is this 2, which is in the position, the element in the main diagonal, rather. Sorry, not the first element. We want to identify the element which is in the main diagonal. Okay? Obviously, the elements of the main diagonals always have the same number of rows and the same number of columns. Okay? What does it mean? It means that when we are in column 1, the element of the main diagonal will be row 1. When we are in column 2, the element of the main diagonal will be row 2. Okay? When we are in column 3, it will be row 3. What does it mean? It means that when we're in a particular column I, okay, the element of the main diagonal there will simply be in position A of I, comma I. Okay, so it will simply be A of 1, comma 1 in this case. Okay, so this is our element. What have we said? We said once we've identified this element, we multiply the row where the element is found, which is this first row. Okay, we multiply the row where it is found by what? By the inverse of that element. Okay, so what will be the inverse of this element? It will be 1 divided by the element itself. Okay, so let me put all of that in brackets so that this happens first. Okay, then we need to multiply it by what? By that row. What is that row? The row is simply A of 1, comma 2 dot. That is the whole row, right? And what does it have to become? It has to become the new first row of the next equation, okay, of the next equivalent system of linear equations. So what we are saying is that the new row 1, which is A of 1 column, okay, has to be equal to the old row 1 multiplied by the inverse of the element of the main diagonal. So that's our procedure that I've written in these terms. And I think you can understand it from everything that we've explained so far. So if I press enter, this is what we get. Did we change A at some point and I was not aware? What happened right here? Okay, no problem. Actually, it's correct, right? Just that it has put 0, 0, 0, 0 everywhere. Okay, so this brings us to formats in MATLAB, okay? The format that you see here is a default format. So the way you would put things with all zeros at the end is a default format to display data. Okay, we will not go deep into it, but we want MATLAB to be able to express our answers in terms of fractions. Okay, so I will just put format RAT. RAT there stands for rational. Okay, and I will press enter. So now when I display A, this is the A that we want, right? We want an A where it has divided the 2 here by 1, okay, and then we have half here, and then 3 on 2, and then 11 on 2. Does it seem like I've misplaced the original A? Yes, we've misplaced the original A, and I would like to keep it somewhere. I would really like to keep it somewhere. So let's navigate through our history again, right up to the point where, or I think it'll be easier to navigate this way because I think it's already really small, and we wrote that thing towards the beginning. Good. So yes, let's keep our original A, and I'll store it in some other variable. Let me call it C, so that we don't lose track of that. It can be helpful at some point. Now we can start our operation all over again. This is A. Okay, we identify the elements of the main diagonal in the first column, and we perform that operation. Okay, so what does A become? A becomes this after we have multiplied the first row by what? By the inverse of this. The purpose is to get our 1 that we have here. Okay, here is half, here is 3 on 2, and here is 11 on 2. Good, we are good to continue. Okay, what is the next step? We conduct elementary row operations on the order such that we have 0 right here. How do we do that? It is this row that we want to change now. Okay, so if that's the row we want to change, we want a new row 2, comma, column. Okay, and the new row 2 should be equal to the old row 2. Okay, the old row 2, right? Plus what? Our reference here is row 1, okay, plus row 1, okay, times what? Times what will actually enable us to get 0 here. It is when we multiply here by -1, right? If we multiply here by -1 and then we add these two equations, this will become 0, okay? So it will be times -1. And when I press enter, that's what we get, okay? We have 1, 0, then we have, okay, 3 on 2, 21 on 2. Clean. So all of this is okay. So with this process, what have we done? We have finished with the first row. We can then move on to the next column rather. Okay, you see how easy it is. Okay, so Before we move to the next column, I would like to introduce a different concept, a different notion, okay? Because so far we've been writing here in the command window. We'll be writing right here in the command window. And all of what we've been writing can only be seen here in the command history, okay? And it executes line after line. Every time we type, it executes. Every time we type, it executes. And we don't really have a follow-up of what we've written so far, okay? So there is a way of actually writing your code in a line-by-line format such that you are able to even save your code somewhere. Because if I close MATLAB right now, okay, and I come back to it to retrieve this code that I wrote all along will be somehow tedious, though there is a different way of doing that with commands like diary and all the like. But what I want is my code arranged in a systematic manner, okay, such that I can edit and review at any given time t. So for you to do that, you need to create a new script, okay. That window is not really visible here. I don't really know why, okay, but okay, let me put it like this, okay. Oh, sorry, okay. So you just have to come here to new, or let me create on this new here. Good, you can still use this. You come to new here and you, okay, type script. So this will open what we call the MATLAB editor, okay. Wow, it took a lot of time there. What happened? So you open what we call the MATLAB editor, this other window. Okay, there is a way of opening this figure in a different window. You just have to come and click here, okay, and go to and click on undock. Okay, this undock will take it to a different window. I don't want to do that because this is the window that is connected to your screen. So I'll just want to maintain everything there so that we finish and we are fine. So here, I have the possibility of writing all of my code before actually executing it, okay, when I'm ready to launch it. So, for example, where is that line where we created A? Okay, so this is our line where we created A. I will come and I will put it here. So these two are different, okay? I hope you're noticing, right? This is the editor and this is the command window. They can be taken as a separate window out of it, okay? So that the command window remains there, but we will not do it in this case. You just need to come here and undock, okay? Good. So I will say A is equals to that. Let me come here to the command window and we will press our CLC in order to have a clean screen. Okay, so look at this. Here I created A is equal to that. Let's try to conduct that operation. Where is the first one? I think this is the first one, right? When we identify, we have to do this. So you go to the line and then you type the next command. So you just write command by command, the same way you would type in the command window, okay? Every command that makes sense, every token, you just write and go down, okay? Good. Where's the other one? Have they gotten lost somewhere? Good. Row 2 now. So you see here I can write without necessarily executing. I will only execute after I have finished writing. And what MATLAB will do is that you will come and execute line after line. Okay. But before that is done, in order to execute this code, you need to run it here. Okay. If you run, this is actually a file. Okay. When you want to run, MATLAB will ask you or will propel you to save first. Okay, so you will give it a name and then you will click on save. So give me a minute. Okay, no, it's not necessary. The window will appear and you will have to click on save. So when you click on save, to give it a name and click on save. The moment you click on save, this is what you will see right here. Okay, you will see a new file that has been created that has the same name as your file that you're using here. So this is actually a file you can use and reuse and share with anybody the same way I will share a file with you at the end of the webinar after we have created our function properly. Okay, so look at this now in the command window. This is where the results appear. Okay, so what do you see here? You see untitled. Untitled is to say it has run, okay, the series of code that is in the untitled editor, okay, and the first line creates the matrix. This is the first line that creates the matrix. The second line does what? A is equal to, it multiplies the first row by that. The third line, okay, does that. You see that? Okay. I can actually type some comments to say what it's doing. Okay. So to do that, I'll use the MATLAB command display. The purpose of the MATLAB command display is to display, right? So we'll just say this is actually an abbreviation, okay? And within, inside the brackets, you just put in between apostrophes, you put the message that you want to display. So here we will say create the augmented matrix, for example. Create the augmented matrix, okay? And it will do that. After it has created that, what we want to say now is we want to say multiply by inverse of main diagonal, just to say something. I just want to show you how we can come out, okay? By inverse of main diagonal, we have that. And then we will say conduct elementary operations. Let's just put it like that. Okay. So if I run this now, what happens? This is the code. It just goes the same way you read a book. Okay, it comes here, it reads this one, executes, then reads that one, executes, then read that one, execute, and so on and so forth. Okay, so where is it? Where is it starting? Let me press CLC and then run the code again. So this is it right here. Create the augmented matrix. That is it. Multiply by inverse of main diagonal. That is it. Conduct elementary operation. It's just executing my code. Okay, good. The other thing I want to show you is this. When you're writing right here, you don't necessarily need to push out every answer, okay? Like A should appear like that, and then it should appear here, it should appear here. That is why MATLAB is showing all of these brownish colors that you see right here, okay? They are not, it's not necessarily compulsory for you to allow these answers to show up themselves. If you have a very large code, allowing these things to echo themselves like that on the command window can actually slow the execution process of your code. Okay, so to avoid that, at the end of every command or every assignment operation, you have to do a semicolon. Okay, you just put a semicolon there. You put a semicolon. You see the way they disappear, right? But when I will run this, what happens is that these answers will not show themselves again. You will just see the display, create the augmented matrix. So this answer does not echo, but it does not mean that it has not executed itself. Okay, it has executed itself, but it did not echo the answer on MATLAB. I could still echo it just to show that it has executed itself. Let's try to say display of A. Let's try to say display of A at every single step, just to show that it has executed the different commands. Okay, so let me run that. You see that? Okay, you see that now is different. It has just displayed A. Create the augmented matrix. That is it. It's no longer A is equal to no, multiply by inverse of main diagonal. Okay, so this one is the display, is this display to show you that it's executing the command, but it's not necessarily echoing the answer. So if you see me writing like that from now henceforth, don't be surprised. It's just because you and I should be lovers of clean code, okay? Clean code implies that when you're writing your code in the editor, you want this here to be green. You don't want it to be red. You don't want it to be yellowish. You don't want it where it has to be no warnings found. That's the way you like your code to be, okay? Good. So that being said, we are already concluding, we are already closing, okay? Because I can see that function coming up already. Can you see it? Okay, so we are in the editor now, okay? And what I want to introduce now is comments, okay? When you're writing your code here, you want to know what you're doing at every single step, okay? The comments is not necessarily the way we're displaying, but comments is that you have a code and you want to know at every level what you are doing. A programmer rightly said that when I wrote my code, it is only God and I who knew what I was writing. Okay, and several months later, it is only God who knew what I was writing, because he came to his code and he could not understand what he was writing again. And that is such a frequent phenomenon amongst programmers. And should you become one yourself after this seminar, you will experience that phenomenon too quite often. So it's important to know how to comment your code, to know that at this level, this is what I was doing. At this level, this is what I was doing. So that whenever you are reading your code again, okay, you can actually understand what you were doing. Or if some other person that you're working together with on that project with that code reads your code, he should be able to tell at this level, this is what you're doing. Okay, so we want to, here at this level, we are creating the matrix. So to write the comment, it's just the percentage symbol, okay, and you say creating matrix. Now, a comment will not execute itself here on the command window. A comment does not execute itself. It's just for the purpose of, it's just for the coder, okay, and for the groups with whom he's working to know that at this level, this is what we are doing. So MATLAB with this percentage will know that this line is not something to execute. He will just keep it and continue executing. Okay, you see it green. Green implies it is not to be executed. All right. So here we're creating the matrix, and here we are, what are we doing again? Inverse, multiply by inverse, and here conduct row operation. So now let's continue, okay? Let's continue with what we were doing. Conduct row operation. But all of this was for what? All of this was for column 1, right? All of these two were for column 1. So for that, I'll create a kind of section. To create a section, this particular section in your code, you just need to double click. Don't mind this. It comes with the new versions of MATLAB. So you just need to put a double percentage. Okay. Let me try to put this down. Good. You just need to put a double percentage, and you say this is column 1. This is to comment your code in a kind of stylish, nice manner. You get the point, I'm sure. So here, double percentage, let's go to column 2 now. Okay, so column 2, what do? We apply our algorithms. We are not stressing. Okay, so it means here I'll go again, percentage, we want to multiply by the inverse of main diagonal. Okay, that's what we want to do again. It's just our code. Okay, we want to multiply by the inverse of the main diagonal. Do we need to stress? No, we just need to take this code, and I'm sure there's just some editing to do there. Okay, so what will happen now? Obviously, at the level of the second column, maybe we should go ahead and see that a little bit this way. At the level of the second column, right, what will happen? It is this element here, okay, that is in the main diagonal, the one in the second row. Are we together? And we will need to divide all of these by the inverse of that particular element in order to get 1 at this level here, because it is 1 we want here, and then 0, 0 this way. Okay, so to do that, we will just go ahead and then put 2 here and 2 here, right? And we want to edit which row? Row 2, okay? And what do you notice? Everything that was 1 has become 2. But we are repeating the same process, okay? Mark my language. Everything that was 1 has become 2. And we are repeating what? The same process. Good. So it means actually we can take this and then we are here, right? So conduct row operation. Yeah, we are here now to conduct the row operation. But here we are on column 2, right? We have already changed row 2. So we have to now conduct the row operation on row 1. Okay. So what do? We simply need to do row. There is a concept we need to change right here. So we'll say the new row 1 will be equals to the old row 1 plus our reference now is what? Is row 2 because we are in the second column, okay? And this negative 1 will not always be negative 1, right? What will it be if it's not negative 1? Well, at this level, I would like us to display the value of A so that we know what we are saying and doing, so that we determine exactly what is supposed to be here. So let me put it here in percentage so that it does not execute itself, okay? And let's put a CLC in the beginning so that each time we run this code, it clears the screen of our command window, okay, before actually running the code. So let's do that. So that's what it has done. Okay, so let's open our command window now. This is what we are having here. Okay, this is what we are having. 1 half 3 2. This is after we have multiplied row 2 by the inverse of the main diagonal. Okay, so we are now here. What do we have to do? We have to multiply this row 2 by the negative of this value here in row 1. Okay, so that when we add 2 of them, what happens? This one has to become 0. I hope you get the logic rather. But what will this value be? The same way this value was, the same way this value will be. What will it be? Well, it's just a matter of patterns. So here, let's remove the percentage back. We are saying the new row 1, this one, will be, the new row 1, rather, what is supposed to be after this one, not this one, will be equals to the old row 1, which is this one, right? Plus row 2 times what? It's supposed to be times the negative of this value here, okay? But what is this position? Let's just write down. What's this position in A? This position will be A of 1, right? Comma 2. Is that so? Okay, so we want the negative of that value. So let's execute this and see if it runs. But now we want to put the display at this last level. Okay, let's run that. This is what we get. Okay, this is what we get. So you see that it has actually disappeared. Programming, guys, is all about patterns. Okay, you'll notice the way I am doing it. I'm trying to avoid to use the numbers that are in the elements as much as possible. I want to use them by the position that they represent because I want to automate the process. I'm using it by the positions because tomorrow I may not have these same numbers. Okay, and if I'm using the numbers, then I will have to be changing the code each time. But if I use the positions, then it is automated. For whatsoever number is in that position, the same operation will go through. Now, this negative 1, you remember on which position was it? It was A of it is actually minus A of, it's supposed to be 2, okay, comma 1. Okay? So the same way here is 1, comma 2. How do I know that? Because 2 here represents the second row, okay? So it is the value that is in the second row at the position of the column that we are concerned with. That's all. So for this case, it's the value that is in the second row for the first column. Here, because it's the first row that we are changing, it is the value that is in the first row for the second column. That's what we want to make 0. Okay, as simple as that. So it means that for the next operation, I don't need to stress. It has become Cramer's rule. Okay, for the next operation, which will be on column 2, this one now, this one, because we want to make this one to be equal to 0, and column 3 rather, sorry, column, come on, row 3, okay, this one here, row 3, because it is this one that we want to make 0. What happens? It is a new row 3 that we are looking for, right? And the new row 3 should be equal to the old row 3, right? Plus our reference row, which is the second row because we are in the second column, okay, times the negative of the value that is at that row in the column. As simple as that. And the moment I run this, what happens? That's a new value, 1 and 0, 0. And it's finished, guys. we've gotten the pattern. If we've gotten the pattern, we can automate. Okay, but let's finish this because that's just what? That's just column 2. So can we rewrite this now without necessarily even looking at whatsoever? Can we just rewrite this? So you see that here, if we are, let's come back to column 1 a bit, because when we are on column 1, where do we want to make the zeros? We want to make it in column, where? Column, oh my God, why am I confusing these terms again like that? Row 1, when we are in row 1 as a reference, we want to make sure that the elements that are in row 2 and row 3 under the one of the main diagonal should be equal to 0, right? So here it will be 3, and here the new 3 will be equal to plus 1, which is our reference, minus what is at 3, right, comma the column consent. That is how simple it is. Okay, good. And then the last one, oh, we can just check up, copy, and then paste. Okay, and if I put here 3, what happens? So that's column 3 now, our reference. So what does it mean? It means we have to go to row 3, okay, identify the element in the main diagonal, which will be 3 of 3, okay, and then multiply its inverse by what? By the old row 3. That is what will give us the new row 3. You see how simple it is. Please, if you are understanding, if you are understanding right up to this point, just type OK. Just type OK. Yo, Chelele, just type OK. Okay, so at this level now, it's finished. If row 3 now is our reference, it means that we want to put 0 at the level of row 1. So it will be row 1, the new row 1 will be equals to the old row 1 plus A3, because now is our reference row, times this way we'll have, come on, excuse me. So this way we'll still have 1, right? Because we are looking at the first element, okay? And then here we will have 3, right? And here will be 2, here 2, here 3, and here 2, okay? And here finally 3. It's patterns, okay? We are dealing with patterns. Right? So that's what we say. Cramer's rule demands that we just follow that particular pattern. Oh, Danny, you are already misunderstanding. Okay? Don't worry, just try to find a way of typing your question somehow. Okay, we'll address it at the end so that we don't waste a lot of time. Okay, so that being said, the code that we've just written now actually can solve any other system. I don't know whether you're noticing that. This one that we've just written like that. Let's execute to be sure that first of all is even correct. Let's display A at the end. Let's display the value of A and execute. Welcome, Queda. Welcome. And execute. So if I execute that, let's just carry that up. And this is what we're having, okay? It has executed. So we have 1, 1, 1, but we have not yet fulfilled our purpose. Remember, we have different types of equations. This one will be able to solve for 3 equations and 3 unknowns with no problem. Let's try out to see whether what I'm saying is valid. Let's just create an equation right now. We want to create an equation where the value of x will be equals to, the value of x will be 1, the value of y will be 1, the value of z will be 1. Okay, the solution set will be 1, 1, 1. So to do that, let's create the first equation. Coefficient of x, we will say 1. Coefficient of y, we will say 1. Coefficient of z, we will say 1. What will be the result? It will be 1 plus 1 plus 1 to give us 3. That will be our first equation. Second equation, let's say coefficient of x 2, coefficient of y 5, and coefficient of z 4. The result will say 2 plus 5 plus 4 to give us 11. Okay. And the last equation will say negative 2, for example, for x, 1 for y, 3. And the resultant will be something like 3 minus 2 plus 1 to give us 2. Right? So this matrix here, let me call it the new A. Let me call it the new A. A. Okay, let's come back to it. Let me call it A. Yeah, it's okay. This is a system that we want to solve. We know the solution, okay? It was derived from the solution. The solution is x is equals to 1, y is equals to 1, and z is equals to 1. Let's now put this matrix in the place of where we created the matrix A right here, okay? And let's see whether it gives us that solution according to what we already wrote down here just by indexing, okay? So let's run that, okay? And what do you see? Clean. Okay, we have identity matrix. The value of x is equals to 1, the value of y is equals to 1, the value of z is equals to 1. So what we've written so far can actually solve any system, okay? 3 equations, 3 unknowns. But it is not enough. We need to actually generalize it to be able to solve for any other kind of system, whether it is 2 equations, 2 unknowns, 4 equations, 4 unknowns, and all the like. So how do we proceed and how do we do that? That's the $1 billion question. Okay. So this is what will lead us to a new concept in MATLAB, okay, which we know to be looping. Okay, let me clear the screen. Why? Because you see here, it is the same operation that we are conducting, okay? The same operation we are conducting over and over again. For column 1, we get that thing and then we do the row operation. For column 2, we get the only thing that is changing is what? Is numbers, because we are going from column to column, okay? That's the only thing changing. Here in column 1, 1 is the reference. In column 2, 2 is a reference. In column 3, 3 is a reference. When we are dealing with row operations, it is the other rows that are not contained with the columns that are the reference, and so on and so forth, right? But it is the same process that repeats itself. So it means that if I have to write in this manner, and I have to do it for a system of linear equation which will be 4 by 4, then I will need to actually write again for column 4 down and then increase a third part. If I have to do it 5, I have to, you see how tedious this can become, and this is where the concept of loops come into place. Looping in MATLAB enables you to do a repeated process over and over in a sort of shortened manner. Okay, we already have all the parameters that we need to put in place to execute our code. We just need to coin it in a certain manner. So now let me explain the concept of loops. And in MATLAB, you have two types of loops. You have the for loop and you have the while loop. So what we will be doing in this webinar will be the for loop, but the while loop is not very much different. Okay, it's really different. Okay, there are relational operators to know to do that, but it's the same concept. Once you have gotten it, you have gotten it. Okay, so okay, yeah, thank you, Danny. Thank you. Okay, so you remember the concept of creating a vector by in this format. If I say v is equal to 1 is to 5, for example, you remember what it does, right? So it gives you, no, let me not go right up to 5. I don't want to see things appearing in this fashion. So let's say 4. Okay, so what does it give you? 1, 2, 3, 4. Let me enhance this concept a bit, okay? By default, you have 1 is to 4. Is to tell MATLAB that you want to create a series of numbers that are separated by 1 from this first element to this last element, okay? So it is 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4. okay? But if you want to change the index, if you want to change the steps between the different elements, you can simply add a new parameter in between the columns. So let's say 1:2:4. This changes the definition of this. Okay, it's still a similar command, but now you're saying you want to move from 1 to 4, okay, with a step of 2. So if I press enter, then I will have 1, 3. So it is 1 plus 2, 3. 3 plus 2 is 5. Okay, it cannot display 5 because 5 is already greater than 4. If I want to display 5, I will need to put it from 1 is 2 is to 5, and you give me 1, 3, 5. This is important. Okay, now looping is actually going through a vector, okay, element by element, and getting the elements of that vectors to do some form of operations. So let me just write the syntax and then we will understand. If I say, for example, for I is equal to 1:4, okay, and I say display I. So notice here there is no command prompt. It means that I'm still in this for. It's not finished. MATLAB is waiting for me. Well, whatsoever you see in MATLAB that is blue like that is a keyword. Okay, it's a keyword, and many times they are followed by ends. Okay, you need to put an end for MATLAB to know that you have ended the keyword. So if I say end here, this end here represents the end of this for, and whatsoever is in the middle is what is in the loop. Okay, so for I is equals to 1:4. It's English language. It's simple English language. So you're saying that let I go through the values 1 right up to 4. And as it is going through those values, each time it goes to the next value, it should execute the code that is inside the for statements. Okay, so the for loop. So if I press enter here, what is it doing? If I press enter here, okay, it has changed my code. Let's do it differently. Let's write what we're supposed to write. Okay, and good. So what has happened? I remember this 1:4 is what? It's 1, 2, 3, 4. Okay, so what has happened? It has taken the value of I is equal to 1 first. Okay, place that I is equals to 1. It executes this code for I is equals to 1, which gives us 1. And then when it comes to end, it goes back and check whether it has finished all of the elements that is in this vector. If it's not the case, it will take the next element, which is 2, okay, execute the code again for I is equals to 2, and it displays 2. Comes again and check, goes back, execute 3, comes again and goes back, execute 4, right up to where there is no element. Okay, so if we change the nature of that 4 and say, for example, 2, 5, the way we just did, and I say display I, and I go right up to end, what happens? It is now 1, 3, 5. I hope this concept is clear, because it will become a little bit complicated as we are entering. Is it clear so far? Please just tell me okay if it's clear. So another way you can use the for is actually to create a vector in front of it. You don't really need to use that particular nomenclature. Okay, so if I create a vector in front of it, I can give the number of the elements that I want to y135 quida, oh la la. It's 135. I said I'll answer the questions at the end, but let me just answer that. Okay, let me just answer that, because 1:2:3. If I execute that, okay, that's wrong. 1:2:5. If I execute that, it gives me 135. Okay, that's the answer. That's the vector that it gives me. So if I go ahead and say for I equals to 1:2:5, then it has to give me it has to go first of all for I is equals to 1 and execute. Let's rewrite all of that command again. display, and then we put end. Okay, so what it will do, it will first of all take I is equals to 1 and it will display that value. Then it will take I is equals to 3 because I is to 2 is to 5 is this is the answer of that execution. It gives you 1, 3, 5. Okay, so if it will first of all take the 1, then it will take the 3, then it will take the 5, and that's what it will just display here at every single loop. Is that clear, Queda? Okay, I hope that's clear. Just say okay so that everybody sees that it's clear for you. Okay, so so far so good. I was saying that you must not necessarily use that nomenclature. You can just say I is equal to, you create a vector right in front here. Okay, to create a vector I can say 2, 4, 5 and 8. Okay, and if I display I again, okay, and do end, what happens? It will display 2, 4, 5 and 8. Okay, so that's very important because this enables us now to reduce our code. Okay, let me show you how. Let's go back to our code. Remember, in our algorithm, we are going column by column. Okay, how do we determine the number of columns of a matrix? You remember, it is simply size of A, comma 2, right? If you want to know the number of columns of a matrix. So, because we are dealing with an augmented matrix, we don't want to do size of A, comma 2. We want to do size of A, comma 2 minus 1. Okay, why? Let me explain that a little bit before coming back here. This is our A. Okay, we want to go through column 1, column 2, column 3, and not column 4 because we are dealing with the columns that have the unknowns X, Y, and Z. Right? So it means that the size of A, comma 2, the size of A, comma 2 will give us 4. Okay, it will give us 1, 2, 3, 4. But we don't want to go through 1, 2, 3, 4. We are conducting these for the first 3 columns. So it means it will be size of A, comma 2 minus 1 to give us those 3 columns. When we'll be in the case of 2 unknowns, it will be 3 columns, but we want to conduct it for the first 2. When we'll be in the case of 4 unknowns, it will be 5 columns, but we want to conduct it for the first 4. So the size of A, comma 2 will always work. Okay, so what are we saying? We are saying that in our code right here, we can just say for, okay, a certain I going from 1 right up to size of A, comma 2, what? Minus 1. Okay, so let me put an end there. So what does this I represent? I prefer, okay, let's just keep it I. Let's just keep it I. So what does this I here represent? It represents the number of the column. Okay, so when the I is equals to 1, we are on column 1. When I is equals to 2, we are on column 2. When I is equals to 3, we are on column 3. But you agree with me that whatever the code I'm putting here with respect to what we just learned, okay, it will execute itself the number of times, as many times as we have the number of columns, as many times as the number of columns, sorry, in the corresponding matrix. Okay, so we want to generalize the principle now because look at, for column 1, we have 1 appearing in some places here. Okay, everywhere that is 1 is because it's column 1. For column 2, everywhere that is 2 is because it's column 2. For column 3, everywhere that is 3 is because it's column 3. How simple is that? Okay, so we just need to get this, for example, and then paste it right here. Okay, so I like clean code. There's what we call indentation. If you don't know this concept in Python, you will not be able to program there. So everywhere that is 1, because I took for column 1, right? Everywhere that is 1 is column 1. Everywhere that is 2, in this case, is column 2. Everywhere that is 3 is column 3. What does it mean? It means that since I copy for column 1 here, and this 4 will go column by column, I just need to replace everywhere that is 1 by I. And when you be column 1, you'll be column 1. When you be column 2, you'll be column 2. So here, I just need to say I. Okay. Here, I and I. Here, I. Everywhere that is 1. Here, I. Here, I. Here, I. And here, I. Okay. But it's not finished, right? Because this case will work only for column 1. Why only for column 1? Because the other operations which are here is 2 and 3. It will always be 2 and 3 because the numbers that are there is actually 2 and 3. Okay? So, but we want it to somehow automatically swap. Okay? So, what will happen? When we are navigating through the columns, we then navigate through the rows. I hope that's what we have been doing so far. Let me come back to our matrix. No, this matrix is not helping. Okay, so we have B. Let me put it clean. We have B. Let's say this is the system that we are trying to solve right here. We have to come to column 1, right? When we are on column 1, we start with row 1. We divide. Then we have to do an operation with row 2, then row 3, right? So when we are in a particular column, we start with the column with the row or having the same number with that column itself, and then we do elementary row operation, taking that row as reference with the other rows. Okay, so what does this mean? It means that we actually need another way also to navigate through the other rows and conduct a similar operation. Okay, why? Let me give you another pattern that you may not have seen. When we are in column 1, right, for example, when we want to change row 2, everywhere that is 2 here is because it is row 2. When we want to change row 3, everywhere that is 3 here is because it is row 3. The other number is because it is the reference number, column 1. I hope you're noticing that. Okay? So, same thing here. When we are in column 2, everywhere that is 2 is because it's row 2. Okay? But the ones with which we want to conduct an elementary row operation, which are row 1 and 3, everywhere that is 1 here is because it is row 1, and everywhere that is 3 here is because it is row 3. And the same principle this way. Wow, that's interesting. What does this mean? It means that we also need to navigate, okay? We need to navigate through the row, okay? So you will have to understand these concepts a little bit brutally right now, okay? Because we will actually have to nest another loop inside this for loop, okay? So what we are saying is that we'll need to say for a certain j, and the j here will represent a number of columns, and we are looping through all of the rows. 1 is to size of a comma 1, okay, and here we will say end. But for me to write whatsoever I want to write inside here, there is another concept that we need to dodge, which are conditions in MATLAB. Okay, so let's look at that. You have the possibility in MATLAB to execute a particular code only if certain conditions are respected. Okay, so an example. I want MATLAB to display. I have a certain value. Let me say I have a certain value. W is equal to 3, for example. Enter. Okay. I want MATLAB to display Loic if W is equals to 3, and display Dimitri if W is not equal to 3. How will I do that? It is simple English language. You don't need to. This thing that I've lied, that I've lied a lot to you guys, that programming is difficult. Many times programming is just another language. It's just another language. You write it the way you feel it. Okay. So if I say if W is equal to 3, let me write it first, then I will explain some things, because you may ask the question why double equality. I will explain that. Okay. So if W is equal to 3. You want MATLAB to display what? To display, I've lost. Okay, good. You want MATLAB to display Loic. Okay. Else is to say if it is not equals to 3. Okay. We want MATLAB to display Dimitri. Okay. And then as for the 4, MATLAB is expecting an end to be able to execute this. What will it show you? It will show you this logic here. That's the answer that it has given you. Why? Because W is equals to 3. Let's copy all of that. Let's change the value of W to maybe 4. And then we copy all of that and see what it will give us this time around. Okay. So if I run that, it gives me Dimitri now, right? Because W is not equals to 3. This double equality you see here is what we know as a relational operators. There are a number of them. Okay. So if I say, for example, 3 is equal to 4, it is different from saying 3 is equals to 4. MATLAB distinguishes them. Why? Because when you say 3 is equals to 4, it's not making sense. It's as if you're trying to force the built-in MATLAB to now change the numeric data 3 to 4. It does not make sense. When you put one equality, MATLAB wants to assign the value on the right to the value on the left. So x is equals to 4 is making sense. Give x the value of 4. That's what it means. But when you say 3 double equality 4, then you make the difference. Now you're trying to compare. You're asking MATLAB, is 3 equals to 4? You're not trying to assign anything. So if I press enter here, then the answer is logical 0. Now this is an update from 2018B, right? Because if you execute it on previous versions, you will not see this logical appearing. The logical here is to be understood as false. Actually, when you say logical 0, 0 in MATLAB stands for false, okay? And 1 in MATLAB, or any number greater than 1, stands for true. Any number different from 0 in MATLAB stands for true. So 0 is false, 1 is true by default, okay? So for example, 3 is not equals to 4. It's a lie. That's why it's putting here logical 0 to say false, okay? So, but if I say 3 equal 3, for example, then the logical is 1, okay? So this operation you're seeing in the middle here that yields logical values of 1, 0 according to true or false are known as relational operators. So what we use is the equality. You can check also if a number is greater than another by just saying 3, for example, where is the greater than symbol? Greater than 4, for example, is not true. 3 is actually less than 4, okay? But to confirm that, if we say 3 less than 4, the same way you write in mathematics, okay? 3 less than 4, yes, that is true, okay? Now, 3 greater than or equals to 4 is also checkable, okay? So, which is false, but 3 greater than or equals to 3, that should be true, right? Because it's equal. And there's also less than, which you can check. Yes, which you can check. And there is 3 different from. Different from is the opposite of equal to. So 3, this is the way you write it, different from 3, okay? Which is not true, because in this case, because 3 is equals to 3. So these are the forms of operations that you will need to write in front of your if statements, okay? Because if will check whether what you're saying in front of it, the condition you're laying down in front of it, for example, when we say if W is equals to 3, it will check if the W is equals to 3, and whatsoever you have put under it is what will execute. If it is not equals to 3, it will not execute what you place under it. It will go and look for a condition that is true before executing. So display yeah, 0, I don't know. Else display. So there is another extension of this. So it will display 1 because you remember our W is equals to 4. There's an extension of this if that includes another else if command between. We will not cover this in this webinar, but what I gave you guys on the links in the PowerPoint will cover that. Okay, so the details are right there. Talia, welcome. She says I'm too fast. You were not there in the beginning, right? Yeah, just coming now. Sorry for that. Okay, so next, this is important. Why? Because when we are in this loop, okay, when we are in this loop, we want to make sure that we are going in for the order, for the other columns, for the other rows rather, okay, for the other rows which are not the rows concerned. On column 1, the row concerned is 1. On column 2, the row concerned is 2. On column 3, the row concerned is 3. Okay, we want to make sure that we are touching the other ones, okay, not this one. So here we have for I is equals to a of I comma column is equals to, here all the terms included there are just I. So there's no need for us to put this term inside this loop. Okay, the terms that we need to enter this loop are these two other ones, the ones that concerns the order. Okay, we'll put them right here, and again let's indent for clean code. So what will this do? This will go to the first column. Okay, for the first column, it will detect the elements in the main diagonal and all the like, and then multiply the corresponding row by the inverse of that particular element, okay, as we want. And then now this other loop is for it to go through the two other rows that are left to conduct elementary row operations. But we need to make sure, because this J is going from 1 to the last row, we need to make sure that it does not touch what? A of I. Okay, so how do we do that? We simply say that it should execute this line of code only if, right, I is what? Is different from J. That's the only case when it should execute this particular line of code. Okay, this one should be executed only if I is different from J, because the case where I is equals to J, we have already dealt with it here. We have already changed that particular row to what we want. The only operation we want there is to divide it by the inverse, multiply it by the inverse of the element in the main diagonal. Okay, so these other ones now, here is very simple. I don't need to put it twice, because it will go row by row for each column. Okay, for column 1 you go right up to 1 2 3. For column 2 you go right up to 1 2 3. For column 3 you go right up to 1 2 3, and so on. So this has to appear just once. Okay, and everywhere that there is 2, I just need to replace by the number of the row, which will be J in this case. Just J. Hey, attention. Okay, and here J, right? So I'm afraid I'll need to delete all of these, or let me just comment that. One never knows. So to comment a whole section like that, let me take advantage and show you that. You just select, okay, and then you right click and click on comment, and that's it. Everything there is commented. It means all of this code will not be executed. The only execution that will be done here will be this for loops. Okay, so let's try and see whether it works for this equation that we put here. Remember, this matrix here is what? The solution is 1 1 1. Okay, so let's run that. Okay, we have not displayed anything, so let's try to display A at the end here. Okay, so when we display A, look at that. It does exactly what we expect, okay? But you see that that very long code has been converted to this very short code. And with this very short code now, we can actually replace any matrix of any size, okay? That means a 2 by 2 will work. two system, a system of equations, a system of two equations with two unknowns will work. A system of three equations with three unknowns will work. A system of n equations with n unknowns will work. So I think we can go back to our benchmarks and then test that out. So this is what we want to try. Why is MATLAB being slow on me right now? So we are closing. We have approximately 15 minutes left, and then we are good to go. Just 15 minutes left. So that is that. So let's create a matrix. We'll call it S1. Hey, we'll call it S1 to check for system 1. Okay. So what will be S1? This is it here. Our solution is 1 and 2. Remember that. So I will say S1 4. Then we have 1, 6, semicolon. We have 1, 4, and 9, right? So that's our S1. Okay, so now in our equation to check if, let's just say A is equal to the S1, okay, to check if it's working. And I'll save that. So let's run that to see the answer. Remember, the solution is supposed to be 1, 2, right? You see that 1, 2. As simple as that. It works now for uh, system of two equations with two unknowns. Okay, so you see we've automated this stuff. Let's now try it for the higher power. Okay, so the higher power will be 4 equations, 4 unknowns, and we have a clean example here. Let's just create it. S3 will be equal to we have 1, -2. Okay, so okay, so we have lastly, I think we're typing the last equation, -1, 1, 1, 1, and then 7. I hope there are no mistakes with this and the connection problem and everything. So let's go right ahead. That's S3. So I just need to replace. I need to replace here by S3, and then we see what that gives. Run the code, obviously. Good. And we have a solution -1, 3, 2, 1, right? Which is the solution that we are actually looking for. -1, 3, 2, 1. Okay. So this code works perfectly, right? So due to time, there's a last section we're supposed to touch, which was functions, how to create functions, but I've put the link on the PowerPoint. It's very simple. It's so simple with everything that we've done so far. We have already automated the process. Okay, all that's left to do is just to create this A as a function. I can actually do it in just some clicks. Let me just do it. So it will just be function. We'll say Z is equal to, how should we call it? I'll call it the way MATLAB calls it, but I'll put a 2 in front. And we'll say of A. And that's it. Our function is there, but here we will not say display A. We'll simply say Z is equal to A. Okay. But if I'm still having all those lines and things like that, it's simply because the name of the function this way is supposed to be the same as the name of the file this way is supposed to be the same as the name of the function. Okay, so I will just close this and then rename this to correspond to the name of the file of the function rather. So which is ref2. Okay, if I rerun that, let's go. Okay, so now you see my code is green. Okay, because actually the name of the function, which is this one, had to. So now if I want to run this code, all I need to do, I don't need to stress anymore. I just need, like any MATLAB built-in function, to just go ahead here and say something like RREF2 maybe of S1, the system one that we just created, and it will give me the answer. Okay, if we say that of S3, that's what it means, function. You just call it and it executes the line of code that you have written there. But you can get more details on the links that are sent to you. So for a dash, obviously MATLAB has a function that executes the Gauss-Jordan elimination method. It transforms any matrix into its row reduced form, okay, row reduced echelon form, and it is simply row reduced echelon form of any given matrix, okay, and MATLAB will automatically conduct that and give you the correct answer as you're seeing here. Okay, so it's just that function that we have created a copy and paste version of the function. Okay, so mm, we have come to the end of this webinar. So I want to thank you very much for being present. I want to thank you very much for being there. It shows that you are actually you are concerned about your studies, you want to learn new skills, you want to grow. So it's a good thing. We shall be carrying on other webinars like that, and you guys that were present here live will receive an email. So stay tuned to your email to make sure that you are up to date with everything that we are doing. Please, you should help invite that conduct the next webinar session, because I'm sure that you've benefited a lot, and you'll be good at the other benefit too as you do, because we'll be organizing webinars more frequently and give skills in various topics. So thank you very, very much again, and I'd just like everybody to tell me bye before I actually go. Okay, so just tell me bye and then we can go. Thank you, doctor. Thank you. Thank you, Raisa. Thank you, Chilen. Thank you, Danny. Thank you, everybody. Thank you. Okay, bye bye.